Hey guys, welcome back to Tech Canon. This is chapter 5, and we're going to be continuing on the series of data structures. Last session we looked at linked lists. Today we're going to be looking at stacks and queues. Oh yeah, we also looked at hash maps last time. But yeah, today is focused on stacks and queues, and we're going to go straight into it. I'd like you to think of stacks and queues by their literal names: a stack of data and a queue of data. But we'll go into details on that. So, yeah, what is a stack? One key thing to remember about stacks is that they use the last in, first out ordering. What does this mean? Simply just means whatever information goes in last is what's going to come out first. So, as you can see on the left, we have 5, 3, 2, 7, 1. 1 was the last one to go in. So if we're taking anything out of this stack, it'll be the first one to come out. That's what that little red line is for, to help you visualize that. So yeah, a stack is a data structure that represents a stack of data. I don't know how else to explain it. So yeah, basic operations with a stack. We have push, pop, peek, and is empty. So with stacks, these are the major operations, and there are a couple others in advanced extensions of like a stack definition. But I'm going to demonstrate how you would ideally add, remove, which is push and pop, and then peek and is empty. So what is pushing into a stack? Pretty much inserting a new item into the stack, which in this example here, you can see we just pushed 2 into the stack. Pop is removing an element from the stack. You remove 2. Peek is kind of like pop, but in that you're not actually removing the element. You're just peeking at what number is at the top of the stack. Taking a quick look to see what's at the top of the stack in this sense. We can peek and see 3 is at the top of the stack. And last but not least is empty. This is pretty much just a helper function to help you check if a stack is empty or not. So if we call that here now is empty, we would get false because we have stuff in the stack, quite obviously. But if it was empty, we get true. So it returns a boolean, true or false. Now, this is pretty much just another demonstration of stacks, but we have some code on the left that shows a stack definition on line 2. We created a new stack of integers, and we have stack operations from lines 4 to 8. So let's walk through these together. So right now we have an empty stack. If you were to call my stack.isEmpty, it will give you true. Your stack is empty. Now let's push an element 5 into the stack. We push 3 into the stack next. We push 2 into the stack next. And now let's pop from the stack. So we pop 2. Pop. And take a peek at who's at the top of the stack. We see that it's 3. Simple as that. So next, let's look at some code for an implementation of a stack using a linked list. So on the left side, you can see some code that demonstrates a stack definition. Inside a stack, every element is represented as a node, and that's what we have defined from lines 4 to lines 10. So in the linked list representation of a stack, each node would have, just like we have for linked lists, we have the data, and then on line 6, for example, you can see we have the pointer to the next element. So let's take a look at line 14. So when we are defining a stack using a linked list, we have to keep track of who is at the top, what element is at the top of our stack. Then we have the push definition, pop is empty, and peek. So let's take a quick look at this representation. On the image on the right, you can see we have a stack that has 4, 7, 1, 5. And if we were to represent that in kind of a linked list for you to help visualize, you would see this pointer from 4 to 7, from 7 to 1, 1 to 5. So ideally, if you want to imagine what a stack implementation using a linked list is like, I'd like you to look at the top of the stack being on the side of 4 and the end of the stack being 5. So essentially, the start of your linked list is going to be the top of your stack. It makes it easy when you have to remove or add stuff. So you just add or remove from the front. Now let's go through each method here. Looking at the push method, this is pretty much just adding an item to the top of a stack, which, if you remember with linked list, if you want to add an item to the front of the stack, all you have to do is add, in this case, say we added 4, we'll add a pointer from 4 to the current top, which would have been 7. So essentially line 17, we create a new node named 4. Then on line 18, we point that new node to the current top, which would point to 7. And then we have to update our top to 4. So now let's say we wanted to pop an element from the stack. How would we do that? So essentially on line 23, we first check if the stack is empty. If top is null, then our stack is empty. And then what we do next is we essentially remove the very first element in the linked list, and then we update top to point to the next element, which you would see on lines 24 and 25, where we set item to the data that we want to pop, and then we set the new top to point to 7, which was the next item on the linked list. Now, is empty is pretty much checking if the stack is empty. How do we check this? If the top element is equal to null, then you have an empty stack. And then lines 34 to 35, where we define peak. When we're peaking, we first check if the stack is empty. If it's empty, we throw an exception that the stack is empty, so there's nothing to peek at. But if it's not empty on line 35, we just return the data without actually removing the node. We just want to view what is in that top of the stack. So next we have queues. What is a queue? Pretty much just a line, as the Americans would say, but the British would say a queue. But the key differentiator between a stack and a queue is that, remember, a stack uses last in, first out ordering, and a queue uses first in, first out ordering. So pretty much just like any line or queue at, say, at a bank or at a restaurant, I don't know, like whatever example you want to use. Whatever goes in first is going to be the first one to come out. Or whoever goes in first will be the first one to come out in an ideal world or ideal situation. Now let's look at operations of a queue. Just like a stack, we have 4 queue operations: add an item, remove an item, peek at an item, and then we check if the stack is empty or not. So one key thing about queues is that it has a constant add and remove time. So it doesn't take any loops to add or remove items. You essentially just add an item to the end of the queue and you remove an item from the front of the queue. O of 1, constant add time and constant remove time. So now let's look at the example where we want to add an element to this queue. We would essentially just append 2 to the back of the queue. Now if we want to remove from the queue, all you have to do is remove the very first element that's at the front of the queue and the rest move forward. Now if you want to peek and look at who's at the top of the queue, all you do is point at the current element at the front of the queue, and you can print that out or do whatever you want, but it doesn't really remove the node, it's just peeking. And then it's empty, just like with stacks. This is just checking if your queue is empty or if it contains any elements, true or false. Next, we're going to look at another definition of a data structure, just like we looked at stacks. This is a Java implementation of a queue using a linked list as well. So if we look at lines 3 through 9, we have the definition of each node, which, just like with linked list, we have the data, we have on line 5 the pointer to the next element, and then we have the definition of a node itself. So in stacks, remember we had a way to refer to the top of the stack, just so we can keep track of what element is at the top of the stack. But with linked list, we're going to be keeping track of who's at the first on the queue and who is last on the queue. So those are the two key pointers we need for our queue using a linked list. So now, for example, let's say we wanted to add an item to the front of this queue. How do we do that? Say we were adding 2. We add a new node 2, which is on line 15, as you can see. Define a new node 2, which is represented by that square. And then to add the item to the end of the queue, you have to add a pointer for the current last, which is 4, to point to the new element. So last would now point to 2. But how do we do that? On line 17, we first check if the last element is null. What we're checking here to see is if we have a queue that contains elements. So if last is not null, meaning there's a last element, all we have to do is update last.next, which in this case would have been 4, to point to the next element, which is 2. So essentially updating the link from 4's next to point to 2. And then on line 20, what we do next is update last, which is where we keep track of what element is last. We move that to last is pointing to 2. So we updated the last to point to 2. Now on lines 22 to 24, what we're doing here is checking if the queue was empty, so we know whether to update the first link as well. So ideally, if we're adding 2 to a queue that had no elements, like what we see on the right, our first would not have been pointing to any element right now. So in this scenario, we would have had to update the first link to also point to 2. And since we have just one element in the queue, it would be the last and the first element. But in our case, we had a linked list representation of a queue that already had some elements. So we don't need to update the first pointer since the first is already pointing to the first element. Now let's walk through a remove scenario. Say we wanted to remove 5 from the list. Lines 28 through 34 of the remove function explains that. On line 28, we have if first equals to null, throw no element found. So meaning if the queue was empty, throw an exception that no element was found. If not, on lines 29, what we do now is we set item to our very first element, which is 5, which is what we see that's popped out of the queue right now. Then we update first to point to first next. So first next, which is 5, was pointing to 1. So now we update first to point to first next. So first is going to move over and be pointing at 1. And last but not the least, what we do here is if the first is equal to null, then set last equal to null. So essentially, if we had moved 5 out and there were no other elements, which is what line 31 is checking for. Remember, that's how we check if the queue is empty or not. If no elements were found in the queue, then update last to null as well. But in our case, we would skip lines 31 to 32 since we already had elements in the queue, and then we'll return 5, which is our element. The other methods are similar to what we saw in stacks. So with peek, we're just returning what data we found in the peek, and then is empty just checks if the stack is empty or not. Now let's look at a variation of queues that is used quite often and sometimes pops up during interviews as well. We have priority queues. So in a priority queue, besides a queue having just a data element itself, it also has a data point that represents the priority of that data. So how I like think about this is like at an airline, or say you're catching a flight. There's first class, then there's economy. So first class has priority over economy on the flight. So they go and get seated first. So they're first in the queue, first in the line. So essentially that's what a priority queue feels like. As you can see on the second image, we have on line 5 the priority as well besides the data point. So with priority queues, like I said, priority is also important to how we add or remove an element from the queue. So let's say in this example, we wanted to add 5 to the queue. And since we're going off priority, In this case, let's assume any number's priority is linked to how high the number is. So the higher the value, the higher its priority. So in a priority queue, if we pushed a new element, we push 5 in, line 53, we push 1 into the queue. Now we want to pop from the queue, right? So ideally we would pop, by queue definition, we would pop 5 out, right? Since it's the first one in the queue. But remember, this is a priority queue. So before you pop, you also check, is 5 of higher priority as well? Yes, 5 is a greater number. So we pop 5 to the front of the queue. I'm sure this looks like a typical queue, but let's keep going. Line 55, we push 7 into the queue. We push 4 into the queue. Now line 57, we have pop. So ideally, if you were to pop from the queue, I'm sure your first instinct would say, of course, 1 is in front of the line, so we pop it. But for priority queues, we're going to look at it this way. 7 is the highest number on here. So 7 is in first class. So 7 has priority over 1. So in this case, if we call pop on line 57, 7 is what will get popped. And the rest of the elements get shifted forward. So ideally, if 2 elements have the same priority, just because of the arrangement of the queue, whoever's in front would still come out first, but priority is checked first before the ordering in the queue. So next, we push 2 into the queue, and that's a simple explanation of a priority queue. Now, priority queues can be implemented using arrays, linked lists, heaps, and binary search trees. We're going to go over trees in the next chapter, and would also cover how you can implement a priority queue using heap data structures. Summary. For this chapter, we looked at the stack and queue data structures. Stacks being a last in, first out data structure, while queues are first in, first out data structures, and how those major operations with stacks, we have push, pop, peek, and is empty. With queues, we have add, remove, peek, and is empty. And then we also looked at priority queues, which is a variation of queues that also takes priority into consideration, where the higher priority items get prioritized first. I know, prioritize. Anyway, that's the best way I could explain it. But yeah, this is chapter 5, stacks and queues. Thank you, and look forward to seeing you in the next session.